Hello everyone, my name is Tapani Sehong and my student ID is 6610755396.
And my name is Sivarak Dongriakun. My student ID is 6610750348.
So we are from LE203 section 750001 of the Interaction of Electrical Engineering Laboratory, and today we will be presenting our Lab 5 experiment on how to use an oscilloscope to observe electrical signals, where this lab helps us to understand both how the oscilloscope works and how to analyze waveforms from DC and AC sources. In electronics, we often need to see what a voltage signal looks like. That's where an oscilloscope comes in. And in this lab, we use an oscilloscope to observe various types of signals, such as square waves, DC voltages, and AC voltages. And also we learn how to set the control to get a clear and readable waveform. So the main goal of this lab were first to understand how to operate an oscilloscope to display different types of signal, and second to observe and understand the behavior of AC voltages using the oscilloscope. An oscilloscope is a test instrument that shows how a signal changes over time. On the screen, you will see a graph. The horizontal axis is the time, and the vertical axis is the voltage. Throughout each step, we use different oscilloscope controls to make it easier to read, such as vertical scale to set voltage levels which contain position for positioning waveform vertically, 1 and 2 menu to display vertical menu selections and toggle the display of the channel waveform on and off, and then scale for selecting vertical scale factors. Next is horizontal scale to set the time interval which contains position for adjusting the horizontal position of all channels. The resolution of this control varies with the time-based settings, acquires to display the acquisition modes, and scale for selecting the horizontal time division or scale factors. And then the multi-purpose menu for many different settings as shown on the screen. But the ones that we commonly use in this experiment is auto set, which is to automatically adjust the view. So we began by checking if the oscilloscope was working correctly by connecting the probe into the built-in test point marked as probe count, and set the voltage division control to 1 and set the time division control to 500 milliseconds, and this produced a 5-volt peak-to-peak square waveform at 1 Hz, and the waveform appears at a series of square steps on the screen. Then we built a simple circuit with a 10-volt DC power supply and a 1 kilo ohm resistor, and then we set the voltage division control to 5, and the oscilloscope was connected across the resistor, and we observed a straight horizontal line at 10 volts, and this tells us that the voltage is constant over time. Even though we change the output voltage of the DC power supply from 10 volt to 15 volt, and with the same setting of the voltage division, which is 5, we still get a flat horizontal line but move higher to 15 volt. After we connected the oscilloscope with a 12V IMS AC source, on the oscilloscope we saw a sine wave with a 40 volt peak to peak and a 50 Hz frequency, which means that the voltage was alternating smoothly over time. We also tested a voltage divider circuit using two resistors, 1 kΩ and 3.3 kΩ. The oscilloscope was connected across the 3.3 kΩ resistor to see the reduced voltage, and we obtained a waveform with a 29 volt peak to peak. And this waveform matched our expectation in shape but not always in exact value. About VRMS and peak to peak. VRMS is the average root mean square voltage of a signal given by this formula. So for a 40 volt peak to peak, the RMS voltage is around 14.14 volt. For voltage divider calculation, we expected about 9.2 volt at a 3.3 kilo ohm resistor using this formula, but we measured 13.13 volt using the oscilloscope, and this resulted in a 42.7% error. And the possible reason that we have the error could be from first, probe loading, second, measurement noise, and third, component tolerances. For a real-world application, oscilloscope help to detect signal noise and faulty components or incorrect voltages. For example, a faulty capacitor might cause an unexpected waveform distortion, and which the oscilloscope can reveal it. In conclusion, this lab was really helpful for understanding how to use an oscilloscope to read electrical signals, and we learned how to first connect the probe properly, second, adjust the display settings, and third, interpret waveform shapes and values. More importantly, we saw how oscilloscope can be used in real-world situations to test and to troubleshoot circuits. And this experiment has made us to be more confident in using test instruments in electrical engineering practice.